Hi everyone. Welcome to our second lecture for week 4. Just before we start, we've got Sarah Grundy from the Faculty of Chemical Engineering here, and I'll unmute her in a sec so you can hear her as well. But she's essentially here to talk about a new course, a work integrated learning course that's kind of on offer, that's super exciting and is kind of targeted at people at your point in your degree. So let me just first check if I can hear Sarah. Do you want to try saying hi?
Yes, hello, testing 1, 2, 3.
Great.
Is
I
all
think
good?
they should be able to hear you. Yeah, so go for it.
Thank you so much. I might share my screen. Um, for some reason, can you believe it?
Oh, do I need to make you a host or something?
Um, yeah, I just real. Oh, yes, I can. I can share my screen.
Okay, great.
Yeah. But for some reason, my presentation is just froze. Can you believe it? Anyway,
Classic.
okay. All right, take 2. I just reloaded the. Okay, so hopefully you can see that now. Is that right,
Yep,
Hayden?
that looks great.
Yeah. Thank you. So I'll just put it on slide mode. Hey everyone, as Hayden mentioned, I'm from a lecturer from the School of Chemical Engineering, but this elective is the idea it is for the Faculty of Engineering. So it is open to all engineering, computer science students and science students that are within Faculty of Engineering. Just a bit of context and background that we get a lot of questions from specifically computer science students who would like to do an internship. And as you probably may or may not be aware, for computer science students, it's not a requirement that you complete internship as part of your program. For your colleagues, in terms of when they do computer engineering, for example, engineering, within the faculty, it is a requirement that they have to do internship industrial training. Because we get a lot of questions on this, the faculty has initiated a work integrated learning elective designed specifically for computer science students as well as food science. Food science is in my school, for the reason that a lot of students do get internships and they would like to be credited with the 6 units of credit for a course. So we didn't have that in place before, but I just wanted to give you a bit of a snapshot, and there's only a quick sort of 8-9 slides that I just wanted to go through that answers hopefully all the questions on this elective. And if you had obviously any further inquiries, you can contact myself. There's my email address, s.grundy@unsw.edu.au. So as I mentioned, the elective is for undergraduate and postgraduate course. The key difference between the two is that the postgraduate level courses are focused on strategic leadership, so sort of the high level management, but in general, the principles are the same in both courses. If you want further details, there's also the handbook, and I'm going to send these slides over to Hayden, so he'll post it up on your Moodle as well, so you'll be able to get links to that. And also there's information on the timetable page in terms of the enrolment details, and there's also a link there that tells you exactly what you need to do to enroll. Okay. Specifically, the program's design, as I mentioned, for in your case, you're probably looking at the second line there, computer science, as a computing elective. And it doesn't matter if you do a combination of these following programs and streams, you would be eligible to take this elective. Okay. The other thing about this is that more from an perspective of the course, the academic teaching content around it is that while most of it is around your internship and work, which is work integrated learning into the industry, there is a academic content that you have to complete in order, obviously, to get a pass criteria for the course. So we offer this in second year undergraduate studies, and the academic teaching content, which is the coursework related, will be around the 3 key areas that we have identified to be the biggest gap in terms of our graduates moving to industry, is around project management, ethical behaviour, and understanding about organisational theory. So the idea about it is going to be useful for you for when you do your placement or even your career later on. There is a requirement that minimum, you have to complete a 15 days of internship, or 50 days is the maximum. And the reason around that is that a lot of companies offer often from 2 to 3 weeks programs through to obviously the sort of 3 months program as well. So that's the reason why. The course learning outcomes, I won't go through this in detail because you can go read it through yourself once I sent you the slides via Hayden through Moodle. But again, as I mentioned, it's around focusing and being able to apply the professional skills and developing that through the academic teaching in the coursework and applying it to your placement in industry. How the assessments are going to be run. So this is the most common question. I've ran this a few times. So the students often ask, what's the assessments like? So this course is not going to be contributing to your WAM. So it's considered to be a satisfactory or unsatisfactory course. Okay, so you only get a pass-fail. And I'll explain the reason why in a minute. But the assessments involved in this course is around having self-paced online modules, and there's a quiz at the end. There's a company report that you have to obviously research about the company and talk about the organisation theory. There's reflection writing. More than 50% of the course marks is through reflection writing. So at each intervals, every 2 weeks, you're going to do essentially a journal log or reflection writing that you're going to build up what we call an e-portfolio. And the idea is that by the end of this course, you're going to have a whole lot of case studies and scenarios that you're going to be able to use for your industry interviews and when you graduate later on. The fourth assessment is a supervisor report. You can see there. This is the main reason why we thought it was not fair to grade you in terms of give you a mark for this course, because there will be a supervisor report from your supervisor in industry in terms of giving you feedback on what you did well and what you did not. And it wasn't fair to get them to mark you because obviously every industry is different and they're not trained in terms of from an academia point of view to be able to consistently grade everyone. So this is the reason why that the course is going to be satisfactory or unsatisfactory only. And then lastly, there's an optional final interview that if you like to do and basically prepare for it, and we'll have an industry panel so that you can practice your interview. Just some key information about the course. It is in the Faculty of Engineering. It is a 6 units of credit elective. Now you have to complete it for undergraduate level at least your 2nd year. So you'll qualify for that after this term. It is considered broad electives. You may or may not know that there's different type of electives, technical electives, which is the in-depth electives. But as engineering and science students, just check with your program streams how many broad electives you're allowed, okay? Because it's different, because it's not an in-depth elective. It's considered the broad elective one. Undergraduate prerequisite, as I mentioned, you have to have completed 72 units of credit. There are multiple modes of teaching. It's blended learning environment because you're going to be doing internship, and then there'll be online and check-in points with the class as well. And if you've done any of these electives, you are not eligible to do this one, because all these electives that you see in point 6 are work integrated learning electives. So therefore, you can't be doing 2 broad work integrated learning electives. And then lastly, this is a key factor, okay? So this course, we don't find internship placement for you. So the idea is that students should have an internship placement even if you get before you even enroll. So then you have to have a pre-approval done through the timetable link that the earlier slides that I showed up, okay? So please make sure you read through these details. And lastly, I've just got one last slide in terms of, I always share with the students, obviously I do a 1-hour talk in terms of internships and so on as well. Again, if you're interested, just email me, I'll add you to the list. But essentially the 5 key things that you should be starting to build up now in your 2nd year is looking at identifying your professional interests and selling points, research occupations and industries that you're interested in, start building your professional network, through student societies, connecting with your academics and industry people that you meet, shortlisting your target employers, and obviously target your cover letter and resumes towards that company. So it's just a really snapshot, of what kind of key elements you're going to get into this course, and obviously we're going to help you develop the cover letter and resumes and sort of build up your e-portfolio for your career as well. Lastly, just as a last reminder, I think this is a common question I get from students, is that, okay, how do I find internships? I always put this slide. This is from the careers advisor, Vicky, is that I was actually surprised to see these stats that 75% of jobs is what we call in the market. So when you see job ads in, Seek or opportunities as such, only 25% of placements is through that. So 75% that where your students and people or graduates get their job is through connections. So headhunters, networking, internal connections. So please don't forget that. And I think in year 2, in particular computer science, is a great opportunities and so much potential and opportunity, not only in Australia and around the world. So start connecting with the various people now. That's pretty much it, Hayden. So it was short and sweet. I don't know if there's any questions or anything that was unclear, but I just thought I'll introduce the elective, and then if the students had questions, they can email me or book a consultation time when they want to. I am a lecturer, so I'm fully teaching, but I am available Fridays for consultation on industrial training and also the elective courses. Okay. Over to you, if that's okay. Is that all right?
Yeah, no, that's great. That's excellent. So there was a few questions on the YouTube chat, but in terms of we don't have to go through them now, but in terms of students contacting you, would you prefer them to all contact you individually, or if you want, we can maybe even put a Google Doc together
email.
where they could all write the questions together?
No, I'm happy for them to email me and basically just understand that maybe allow me at least 48 hours to get back. I do teach a lot of courses. So if you look at Sarah Grundy up, I do all the design courses in chemical engineering. So, and currently term 2 is my shortest time, but if you email me, I'll definitely get back to you and we can book a consultation time. I'm sorry, I'm working at home today.
No, that's all right. Little girl here. That's all good. Yeah, so we'll pass on the slides and your contact details. That sounds good. That's all good. Thanks so much, Sarah.
Thank you so much, Hayden. Thank you. Bye-bye.
See ya. Cool. Hi everyone. So I'll just be passing on those details when I get them. I will be putting it up as a notice here. I won't send it out as an email though. I don't like to clog your inbox with emails. So if you want to see this, if you're watching this lecture now or you're watching it later, it'll be one of the notices that are sent out. Sometimes I put non-critical things up here. Yeah, so cool. That looked really interesting. There were some good questions there. I have to say though, without getting, I mean, today's actually a pretty light lecture day, which is good, but without getting too lost in it, I do like her slide around the job market stuff, because like I didn't really know any numbers with it. It's something that's always been on my mind, right? As a lot of students get really stressed about internships because they go to these like little careers markets or something, and they see like these 8 tech companies and then they all get rejected from them, and it's like that's a tiny proportion of the market out there. I actually think that slide that Sarah had around like the job postings is actually, my instinct would tell me it's actually even more is hidden away in the software space, because nearly everyone is looking for software engineers for something. Like I would struggle to, everyone can kind of use it. So if you ever do get stressed about work placements, just remember there's a lot of work out there. Sometimes you just have to look for it, because the stuff that you see is just the stuff where companies are basically just paying to steal you. So don't get too stressed about it. But let's move on. So this lecture formally is the beginning of the B Trees lecture. And we will do the B Trees, but we had this thing with Sarah at the start. I'm going to chat quickly about AVL Trees, and then we'll do B Trees for like a while. For the last half hour or so today, we're going to go through assignment 1. Kevin Luxa, our course admin, is also going to join us via Zoom like Sarah was, to essentially go through assignment 1. Because as I've said to you, like Kevin and I ran through the assignment together, but the difference between me and Kevin is that Kevin has both taught this assignment before, like managed questions with it, as well as actually, marked it talked to students through it, gone to help sessions about it. So while I understand the assignment, there's always like, you know what being a student's like, right? You have like these little mini questions everywhere. Kevin will be a lot better prepared to answer those questions because he's like me, but better at things. So we're gonna first run into just the tail end of, oops, that's the wrong slide. We're gonna run into the tail end here of AVL trees. So one thing that came up yesterday, and James was in the chat here yesterday when we talked around the AVL tree algorithm. I'm not going to talk about this now, mainly because like AVL trees and B trees and all these other things, sometimes we teach you things that we can't step you through everything, and mainly because we're not going to assess you on it like super aggressively. Though there was some questions about this double rotation behavior here. So with an AVL tree, if you remember from the last lecture, AVL trees focus on kind of localized updates in particular, and that is how they can, here you go, do repairs on tree branch locally, not on the overall structure. So the idea is if you can do local repairs often, you don't have to go and do like 100 rotations on a tree, which is great. So one of the ways they do that is just by doing a little rotation after insert. We went through a bunch of those examples, but if you read the pseudocode, sometimes there's like a double rotation that happens here, and that's what you can see here. Now, there's no way in a few minutes I could explain this to you and like draw it out, because I'd probably want like 15-20 minutes to do that. Though one really great thing, and we'll do this for B trees later today, is if you Google visualization algorithm, and you go here, pretty much all University of San Francisco, I think that's University of San Francisco, California.edu. They have a whole bunch of these visualizers. They have it for B trees, which we're going to talk about today. And what's great about this is if you're ever looking at a pseudocode and you're trying to really make sense of this algorithm, and this is an inserting algorithm, you can essentially actually just start inserting nodes into a tree here and try and make sense of what happens. So, if I insert 10 and then I insert 5, and then I insert 15, you can see it's actually keeping track of, well, they're using, like, this is kind of like height here, but, we were using zeros and ones. But, if I started inserting more now, like 18 here, the tree will continue to grow. And if you remember the AVL algorithm yesterday, the idea is that the height of the two children can't differ by more than 1. So you see this node up here has a 1 and a 2. They differ by 1, but the second I add in something like a 20 here, the tree heights will differ and there'll be a rotation. There'll be a rotation about the 15 here, because I believe, or the 10, sorry, 10 or the 15. Yeah, about the 15. So you saw that we just did a rotation there with the 15. Now, so in the algorithm here, that was, what way did we rotate there? We rotated left. So that part of the algorithm here was actually this thing here, I believe. But this line here wasn't executed. And essentially what this if condition is it's saying that anytime you insert into a tree, and I'm going to do my best to explain this, there's kind of like a zigzag at the bottom of the tree, you have to do 2 rotations. So I think we'll see this if we try and say insert 16, potentially, where we create a zigzag here. Yeah, so that was a double rotation. Now, that's one of those things you want to kind of step through slowly. And again, my job here is not to talk about it. So until you get it, it's like to show you how you can go away and look through this in your own time. But essentially, whenever you do an insertion that forms like a zigzag pattern, like a right then a left or a left then a right, you'll tend to see a double rotation. And we probably see it here again if I do a 19, which will create an 18, 20, 19 zigzag. There should be 2 rotations here. It does it all really quick. Oh no, it's fine because it's not in balance. Sorry. But if I do I've screwed myself with this tree. Damn it, that's okay. Play around with it. Anytime the tree becomes imbalanced through a little bit of a zigzag thing, then you'll see it do a double rotation, and just really spend the time going through the pseudocode here. So just a couple of questions on the forum before we get into B trees. So one a while back, Waleed says, would you say that is it true for big firms, like big companies that they hire internally a lot? Um, Without going into a whole spiel in the middle of a lecture about industry, a lot of big tech companies have a massive preference towards hiring some PhD grads, and then doing some horizontal hiring of other people who are already trained at other tech companies. And they have quite structured programs for that, and they'll headhunt, but typically they're looking for people who are trained if you're not a grad. Um, and that's true for probably a lot of big fours and stuff. I think it's more like there's a lot of software that happens out there in the kind of like small to medium space. Like examples I give are, like I live in the Canterbury Bankstown Council area at the moment, and I'm sure like the local council probably hires software engineers to do stuff for them, or they hire some consulting like contracting firm that like there's just kind of stuff out there. Um, and honestly, most people I know that get really interesting jobs, they just end up talking to a lot of people. Like I had a friend, I won't give you much detail about them. They were trying to get a job at a bigger company, quite a big company, and they didn't get rejected. They got like kind of slow rolled by the company, and they were a little bit jaded about it. And while they were waiting to figure out what was happening with their job, because they were basically like unemployed, graduated, they went and worked in retail for 6 months just to pay the bills. And while they were in retail, as they were chatting to people every day, um, they was, someone's like, oh, what do you do? And they're like, oh, I'm just doing this between jobs, and this is the industry I'm interested in. And most of the applications they applied for after that ended up just being people that came into the retail store who were like, oh, I heard so and so is looking for a grad in that area and stuff like that. So there's actually a really interesting and diverse world out there if you um, you know, take your head out of the rock kind of thing. So it's just something to think about. I don't want to get into that because there could be a million questions. So I probably won't answer any more questions on that for the moment, but keep asking throughout the course. Dear Aurora says, would it be possible to get a PDF version of the assignment? Yeah, you can pretty much save pages as a PDF. And I know it does ruin some formatting, but it's like, that's, if you ask for PDF, I would just print out the page as a PDF. Cause, or I would copy and paste it all into Google Docs or something. It's kind of something that could be done by, I mean, any way I would do it, you could do it kind of thing. And unless I started getting like a half dozen people asking me for a PDF version, I'd probably just leave it as it is. But feel free to export it as PDF or whatever. Okay. Now, I can take my headphones off. I don't need those. Oh, that's so much better. Whew. I feel free. So, this topic, which is what this lecture, how many minutes into this lecture are we? We're 23 minutes into the 234 trees lecture, and we haven't done anything on 234 trees. So 4.3 is about 234 trees, which is the last type of tree we're going to be talking about in this course. I've referred to them a couple of times as B trees instinctively because B trees are a topic that covers lots of these tree types, but today we're focusing on a particular type of this B tree called a 234 tree. So if I say B tree instinctually, I mean 234 trees. It's all the same. This will make sense at the end. But we're talking about 234 trees, and the reason that this tree is interesting to us is because a normal binary search tree, as you know, is like node, two children, and it kind of ripples out like that. One of the problems is that a lot of the cost of traversing a tree comes from essentially like how deep the tree is. Like, and you've probably seen this as well when we look at algorithms of, how what's the time complexity of a tree. And the answer is often in terms of OH, the height of the tree, or O log n, which is, the log of the number of nodes in the tree, which is often the height of the tree. So most of the complexity blows out with that. And we want to try and solve that problem through a more complicated data structure. And that data structure we're looking at is called 234 trees. Now, when I just talked about the search cost, this is just a bit more of an elaboration on what I just said briefly. A big part of what makes your tree big is what you call the branching factor. And a branching factor is basically how many children can a node have up to? And when it comes to binary search trees, those are a type of tree that has a branching factor of 2, because you have a node with 2 children. What we're looking at now is a type of tree, a lot like a binary search tree, same general rules, except instead of a node having one item in it, like a number, and 2 children, a node can have a few items in it and up to 4 children. So essentially a lot more next pointers. And you could imagine the idea of this, just before we get into it, is like, instead of having a tree that's like this, where it just keeps going down. Oop, that was random. I think I just hit play on a YouTube ad. Instead of having a tree that just kind of goes down like this, where each one of these has a number in it, what we're going to be looking at today is a tree where each node has a few numbers in it, and it can have potentially up to 4 children. So what you get from this is a tree that's kind of the same size, in the sense that it has all the same numbers in it, but it's a lot more dense, because you're not just like branching out constantly by a factor of 2. Now, the benefit of a tree like this, or one of the immediate benefits of a tree like this, is pretty straightforward. When we look at the time complexity of trees, what we tend to do is we say log n, or log n gives you the complexity of traversing a tree, right? Because log n is the height, because the tree branches out, base 2. In reality, the log that we should be using is a log 2, because it's base 2, right? So it's the opposite of a square function. It's like constantly square rooting that number, and seeing how many times you have to square root it to get back to 1, or something like that. So you can see that if we have a tree with 4,096 items in it, and it's a perfectly balanced tree, that's a height of 12. It's going to be 12 steps in the worst case to get to the bottom. This 2 here represents the branching factor, because it's a binary tree with 2 children. Now, we've also told you previously that it doesn't matter what the log base is, because log 2, log 4, log 8, they're all logarithmic in their growth. It's just that the coefficient is different. So a log 2 function grows quicker than a log 4, but they're all logarithms, and it's just a variation of it. Just like 2n and 3n and 4n all realistically do grow quicker or slower than the other, but they're all n, so we generalize them with big O notation as n. So a tree with a branching factor of 4 here, like these 2, 3, 4 trees we're talking about, or the ones I just drew up for you here, these ones still have a log n time complexity, a big O notation, but in reality they're a little bit quicker to traverse, because the log is a 4, right? Because essentially, if you got 4 children, it's a log 4, and if you got 2 children, it's a log 2. And as the number of items within a node gets bigger, as I put more stuff in here in each node, and I add more branches, the tree in theory has less steps to go through. Like that. Now, there's a great question that I just want to reference. I won't talk about it yet. So, Kaustub, I'm not sure how to pronounce your name, sorry, says there are fewer steps, right? Sure, I get it that the tree's flatter, but we're just chunking out each node. So wouldn't the time complexity be the same? Sort of. I mean, let's come back to this. That's a great question. I think like all these things, the answer depends on certain use cases. So my understanding of it is sometimes, yeah, it does result in the same. Sometimes no, it can be a lot quicker. It really depends on like use cases. You know how we normally do best case, worst case, average case? Yeah, so let's keep chatting about that. But that's an excellent question. Jeremy says, so can a node have 2, 3, or 4 children? Yes, so a binary search tree node can have 2 children, 1 children, or 0 children. A 2, 3, 4 tree node can have 4 children, 3 children, 2 children, 1 children, or 0 children. Okay, so it's the same concept, it's just it can be bigger. It has a bigger branching factor. That doesn't mean it has to branch 4 times, it means it can branch up to 4 times. So it is in effect quicker because you have less steps. So it would still be log n, because it is still logarithmic, right? Base 4, base 2, it doesn't really matter. Big O complexity, big O notation would say it's log n, or log h, where h is the height. But again, it might actually be quicker in reality. So this ties into that topic where big O notation is a bit of a simplification of things to convey a general idea of how an algorithm generally behaves for large inputs. But reality, we do a bit more digging. So this is a 2-3-4 tree. 2-3-4 trees have one of three kinds of nodes, either 2 nodes, 3 nodes, or 4 nodes. Now, if they have 1 child or 0 children, we'd probably still call them 2 nodes, I think, because it's just kind of like a normal binary search tree node, which is why you have this one here says 2 node, even though it has no children. But often the 2 nodes refer to, how to put it? So the diagram's somewhat self-explanatory, but if you want to think about what to call a node, typically look at the number of elements in a node, add 1 to it, and that's your node. So this one has 1 element, so it's a 2 node. This one has 2 elements, so it's a 3 node. This one has 3 elements, so it's a 4 node. In reality, what's actually happening here is that it's saying that this node at the moment is a 2 node because in its current state, it can only have 2 children. And I think I've glossed over a pretty critical part here, which is that if anyone, I'm surprised no one's actually asked this question yet, which is, okay, I get that maybe they have a few children, I get that maybe there's a couple of items per node here, but how is this actually structured together? And the answer is that it follows a pretty straightforward rule, which is that if you have a 2 node, like a binary tree, everything to the left is less than it, everything to the right is greater than. If you have a 3 node, like this, then everything to the left of x is smaller, everything to the right of y is bigger, and everything between the two is between x and y. So, you could kind of imagine all the children of this slot in between the items in the node, and they all form that same kind of perfect balance as a binary search tree, whereby you have that confidence that, everything here is of a certain type, everything here is of a certain type, and you have those guarantees of ordering. So it's still an ordered data structure. It's a little bit more subtle because you kind of have these like little in-between trees here. And you can actually see this in the alphabet example. So you'll notice here that you have this node J which has a right child. So everything over here is less than J. But on this little 3 node here, everything left is less than N. Or like when I say less than N, I mean like further to the start of the alphabet than N. Everything between N and T has to be between N and T in the alphabet, and then everything to the right of T has to be like after T in the alphabet. So that there is this ordering that still applies. Joshua says, so why stop at 4? I don't know, why stop at anything? I mean, this can be applied for a lot of different kind of data structures. Often, sometimes you want the benefits of things without the hassle. Sometimes, again, let's come back to these use case questions, because I think as we talk about these more, it'll make more sense if I give you specific examples. So we've talked about the tree structure, and a balanced 2-3-4 tree has all the nodes the same distance from the root. All the leaves, I guess that should say, probably. Maybe that should say leaves. I'm just going to make a quick note of that, because I don't know if all nodes the same distance from the root makes sense, but cool. So that's the kind of general structure. Now, where 2-3-4 trees get probably most confusing is when it comes to the insertion. I think structurally when you look at them, they make some sense. You're like, okay, it's like a binary tree, except it's got a few items in it. And the general approach, just trying to think about how I'd word this. There's a few different ways I've seen people explain how to insert into these 2-3-4 trees. And it follows a very similar pattern to inserting into other types of trees where you start at the root, which is where all trees start. You go down and you find the spot that it's going to get inserted into. And then as you unwind, you restructure the tree to maintain a sense of order. So it's kind of like what we talked about with AVL trees, and it's kind of what we've talked about with insertion at root and other things. So it goes down the tree, finds the spot, says great, and then as it unwinds, it maybe restructures some things. The way B trees work, 2, 3, 4 trees work, same thing, is that when they go down the tree to insert something, if the node they're inserting in is not full, i.e. it has less than 3 items, it gets inserted into the node. So if I do, I'm going to do B tree visualization. Because remember, B trees are just, 2, 3, 4 trees are just a type of B tree. And all these links, I think, by the way, are chilling here. So the visualization of B trees links just on Web CMS 3. Well, it's a page that, I don't know why we have that instead of just linking it to you. So you'll see here, this is the page where you can build a 2, 3, 4 tree. Now, what you'll see here is there's this max degree thing. Now, 2, 3, 4 trees are trees with a degree of, B trees with a degree of 4. So in these slides, we talk about 2, 3, 4 trees, but they are just B trees with a degree of 4 because 4 is the maximum children you can have. Okay, so you could obviously have different types, but that's not a 2, 3, 4 tree. It's called a 2, 3, 4 tree because it has 2 nodes, 3 nodes, and 4 nodes. Like, they're the name of it. That's why we call it 2, 3, 4. Now, again, the approach is that if the node of if your node you're inserting into is not full, then you insert it into that node in a list. This is quite, I guess, different from a binary search tree because in a binary search tree you have one node with one item, whereas in a B tree you have one node with up to 3 items. So if I insert, say, 20 here, I'll create my root. And then if I insert 30, what it's going to do is it's going to, according to this, if the node of the insert that I'm trying to insert it into is not full, insert it into this node in the correct location. So it adds it there. Now, this I think is one really kind of key difference between a binary search tree and a 2, 3, 4 or B tree, is that with a binary search tree, you find, like, when you insert something, you typically get to the bottom of the tree and then you insert it into a new null space, like a child. So, you know, you find your 20 and then you insert it down here to the right or to the left. But with B trees, you're nearly always trying to insert it into the node itself. So you find the node at the bottom of the tree where you can't go any further, and then you try and insert it into that node. An important part about this is that you always insert it into the node in order. So you'll see that when I started with 20 and I added 30, it added it to the right. But if I add 10 to this tree, it's going to add it to the left. So the actual node, the actual items in a node are ordered in nature. That's just essentially how it's structured. And this makes sense because that's the only way you could have a tree where, you know, you have every, like, a branch here and then a branch down here and then a branch between these two and then a branch at the end. Okay, that's the only way you could maintain that kind of ordered structure. So the first case of inserting into a B tree is very straightforward. Case 2 is the kind of more tricky case, which is what happens if you try and insert into a full node. So if you try and insert into a full node into a 2, 3, 4 tree, what happens is that the node is split in half, and what you do is you apply checks to the parent recursively until there's no more splitting. So this is something I think we're just going to have to go through a few examples to make it clear to visualize. I don't think I put any. I did put some visualizations. Let's look at this stuff in the slide first. I'll come back to a few of these questions here. So if you have a 2, 3, 4 tree like this on the left, and then you insert a k into it, it's going to go traverse down the tree, and it's going to go, well, I'm greater than f, and it's going to come here, and then it's going to say, okay, let's see if I can fit inside this node here, because it's not full. So it's found the bottom of the tree, it's not full, j and m, I say, well, I'm less than j and I'm greater than m. Okay, so what happens here is that it gets slotted in between that j and the m. In the next case, if we take this tree we've just added k to, and we look at oh, this is a different tree down here, sorry. If we look at a second tree like this, where we have f and j at the root, we have 3 children, and those 3 children are 3 nodes, 2 node, and a 3 node, a 2 node, and a 3 node, and then we try and insert h into that tree, a very similar thing happens, where we say, okay, well, let's try and insert h. Let's look at where h can be inserted. We look at the root, we say, okay, h is greater than f, but it's less than j, so we go down here and we try and insert it into the child. There are no children of this, so it's going to try and get in the node, so that's why it gets inserted after the g here. So you're always trying to find the bottom of the tree, and then you try and insert into that node at the bottom of the tree. The more interesting example, which I'm about to go through on the visualizer as well, is this idea of a node split. And this is essentially what happens when the node you'd like to import it into, or like add it into, is already full. It already has 3 items. I do want to quickly answer Jeremy and Autumnal's question. So Jeremy says, can't it just go between f and j? Well, it could, I guess, but the point of this algorithm is that you're always trying to insert into the bottom of the tree. Like, I don't see a reason it couldn't go there. I mean, it could go there, but you'd be dealing with a different kind of tree and a different kind of algorithm with different kind of characteristics. Okay, that's kind of it. So yeah, you could put it there, but if you really tried to apply that rule consistently over and over again, you would notice that your tree goes really wacky really quickly and some things don't make sense. So in a vacuum, I get your question, but that's not a sustainable way to grow this tree, and it's not kind of the rules of this tree. So again, just to reiterate to you, it's always trying to go to the bottom of the tree first, right? Like a binary tree, when you insert it, it goes down to try and find the one of the leaves, and it always wants to insert itself at a leaf. That's what it's always trying to do. Kenny says, what exactly is the degree of a tree? The degree of a tree is the maximum number of nodes. I thought it was a 4. Maybe, I think it's 4. It's the maximum number of children, I believe. We can try this out pretty quick if I try and insert 40. Yep. So it's the maximum number of children is how I think about it. I think it's a bit confusing because a degree of 4 makes you think like, you know, it has 4 items in the node, but degree is another way of saying branching factor. Order is another way of saying branching factor. But again, I don't want to, this visualization's interesting, but I want to take you through the step here. So we've talked about when you're in, like, every single insertion starts at the root, you go down to a leaf that is relevant, you try and insert it into that leaf. If that leaf is not full, you just slot it in. That's what happens in these 2 examples here. The more tricky case is what happens if, let's say for this first tree over here, up here, if I try and insert, say, something like Z into this tree, it's always want to go to the leaf, right? So not the root. Every time we get asked, like, why are we not inserting it here and there, it's like you always try and insert it at the leaf. You always go to the bottom of the tree, the very bottom of the tree you possibly can, till you can't traverse any further. So in this case, if I try to insert Z, I'm going to look here, I'm going to say, okay, this is not the bottom of the tree, I'm going to go right, and then it looks at this node here, which is like a leaf, and then I say I'm going to insert Z here. But the problem with this case is that the node is already full. So that's where the second case of, like, if it's already full, we have to do a node split. And a node split, let me go through the example first, and then we'll come back to the theory of it. But a node split's really, oh, it's funny, I didn't realize that was the exact example we were going to use. A node split's really interesting because what happens is if you try and insert a Z into this tree over here, okay, so we've got this 2, 3, 4 tree, and I want to insert a Z. We start at the root, we go here, and then say this is the point where we're ready to insert it into. Okay. I'm gonna not answer some questions for a bit because I feel like I'm also confusing people listening by jumping around topics and simplifying things. Let's look through the algorithm and then I'll come back to some of these questions. So when you have a tree like this, you try and insert it into this particular node here. But what happens is because this is full, what you do is you basically do insert it into that node. You do put a 4th item there, but as soon as you put the 4th item there, you split it out. You split it in half. So what happens is you literally take the node and you rip it in half, and you promote the middle element up a layer. It's a very, very strange little step, but it's extremely deterministic and extremely straightforward. So what happens here is that the second diagram shows it in a bit more detail. If I try and insert the Z here, it ends up trying to be inserted here at the bottom of the tree, but because the node is now full, we split it in half. Now, 2, 3, 4 trees are weird because when we say we split the node in half and we promote the middle element up, the strange thing about that is that we have 4 nodes. So how do you split 4 nodes in half, right? Because we've got J, M, R, and Z. And the general convention here is that, you know, just like in C with flooring numbers and stuff, you just take the thing on the left of the half, which in this case is the M. So what happens is that we have 4 elements here, right? Because Z tried to fit in and it's already full. So we split it in half. We take the middle element as we split it and we pull it up a layer. And it's the M, not the R, because we take the thing on the left of the split. And then that M gets moved up a layer in the tree. So just paste through that again yourself. If you try and insert a Z into this, it's going to get the 4th item, too big, splits in half, middle element go up, and the middle element literally goes and sits in the parent's node. So that's a node split process here that happens when you're trying to insert into a full node. Now, it's a pretty straightforward thing. There's no tree rotations. There's no weird things like that. Though the question that's going to come to your mind, which Jay said here, is what happens if the parent's node is full? What happens if, okay, this thing down here is full, so I insert Z into it. So then I promote M up because it's full, but then where M goes is now full. So the layer above is now full. Well, what actually happens is that exact algorithm is applied recursively. So then if the layer above was full, it gets split up again. Autumnal says, why did Z get added with R and not as a child of R? Again, let's come back to that when we look at the pseudocode, because this diagram could potentially be deceiving. But just ignore these little lower nodes here at the moment. Basically, we put it in at the bottom. It's just how I'm explaining it at the moment. But we keep applying this split recursively. Okay, and this actual thing here, this is an example here of some recursive splitting. Yep, where if the root node is full, then it just keeps splitting. So in this case here, if we try and insert N into this particular tree, N fits between J and R, so it tries to go down this little route, this little path, and then it finds the node it wants to get inserted into, so it inserts itself, K, M, N, P. But because that node is full, we split K, M, N, P here in half, where you have K on the left, N and P on the right, and the M gets sucked up one layer. So if I was to maybe just like, I'll do this in Paint real quick, even though I'll butcher this pretty bad, I can feel it. So what happens here is you try and insert an N, and the N says, well, I'm between J and R. So the N says, oh, I'm going to insert myself in this layer here. So it goes, yep, I'm an N, I'm going to go here. But the problem is this particular node here is now full. So it says, oh, we're going to have to split. We're going to have to split up. So it goes, yep, I'm going to split up. We're going to separate about M, and then M is going to get moved up a layer, and it's going to go up into this node here. I'll move that in the right place in a sec. The problem is now, though, well, what would actually happen here is that this, yeah, this is what I was worried about. This M would get slotted in here, like this. And then all these little things here would get rearranged. Trying to get rid of this one. So this point is the M gets moved up and it gets put in the right place as well. So then what we get left with is essentially like the same problem but a layer above, where this is what the tree looks like now. But it's full, right? So we split M, we moved it up. The things we split are the children on either side of M. Do you notice that? You notice how like before when we had M down here in the node, like this, when we split this node in half and moved M up, the two halves are the children either side of M. But the problem is this node is now full, so we have to do the exact same thing we did before, where we say, all right, M and R is on the right-hand side, F is on the left-hand side. We're going to have to split this and bring J up here, and then J comes down like that, and everything makes sense because M and R is a 3 node with 3 children, F is a 2 node with 2 children, like that, and then this tree works fine. And naturally these things here are on the same layer, I just like didn't draw them great. Kind of looks like that. The way I like to think about B trees, or 2, 3, 4 trees, is that, and this is just my way of thinking about it, I like to think about it that they grow upwards, right? And I'm sure other people think about it like this too, is that they're essentially trees where if I was to try and visualize it, in my head, the leaves are always at the bottom and the tree just kind of grows up. So you start at the root, you try and insert into the bottom, but as the bottom gets filled up, it keeps like growing the tree vertically, as opposed to like a binary tree where you're often thinking about the tree as the root and you're just like growing it downwards, like thinking about it expanding out in that direction. So like building a pyramid. Yeah, exactly. And it's a really interesting tree structure because what it actually guarantees you is that all the leaves are on the same level. It's a very strange phenomenon that I'm pretty sure it guarantees you that. Yeah, it does. Yeah, it's peculiar like that. I think it said that somewhere. I remember when I read that the first time, I was like, oh, that's kind of strange. Yeah, so cost of building must be high. Yes, like a lot of trees, the cost of the splitting would be constant time. But it's how many times you have to apply that. So if you have to split every node back on the way back up, then deletion is like is well, here's the funny thing about trees, right? Pretty much all tree inserts, oh god. Pretty much all tree inserts are OH. Even a binary tree inserts OH. Makes sense. Worst case is you have to go down to the bottom of the tree. A 2, 3, 4 tree, an AVL tree, all of these have a worst case of OH as well. Because you always have to go down to the bottom of the tree, but in the case of a 2, 3, 4 tree, for instance, all the node splitting is also another OH. Because in the worst case, you not only have to go to the bottom, but you have to literally restructure everything. But because each restructure is constant time, and you're doing it on the entire height, it's OH as well. So what's OH plus OH? Well, it's OH. So most operations on trees are OH. That's the cool thing about trees. But the reality is that this would take longer, physically. Because 2H takes longer than H. It's just minor in the grand scheme of describing the general behavior of algorithms, which is what big O notation's about. So yes, it is more costly. It's not going to come out in the time complexity though, in the big O notation. We're going to probably finish this off, and anyway, we'll see. Maybe we'll take a break in a sec, but let's see how we go. This is a 2, 3, 4 insertion here. So you'll see what happens is the tree might start off with 3 nodes. And then what happens is if you try and insert a C, it splits and so forth. Now I don't want to go through this because this one doesn't show you intermediate steps, so I think you might need to just stop and really look at this for 5 minutes. So like the red numbers are all what's inserted, except each step shows you what happens after the modification. But let's just play with the visualizer again quickly, because I want to insert some numbers. So let's insert 50 and then 20 and then say 80. Now you'll see, oh, I did the wrong degree. There we go. So we insert 50, 20, 80. You can see it inserts them in order. Okay. Now watch what happens. If I insert, say, 60, what's going to happen is 60 is going to get put between 50 and 80, but the node's going to be full, so it's going to split it and pull the 50 up. So if I insert 60, you'll see it'll add it and then split it and pull the 50 up. And then if I insert something like 25, it's going to keep building out the leaf here, like that. And if I insert, say, 30, it's going to keep building out that leaf. And then as you see, if I insert 15, it's going to try and put it into that same leaf node, except the node will now be full. So it will split it with 15 on the left, 25 and 30 on the right, and then it'll pull the 20 back up. Like that. And this will keep going. So now if I say insert 70, it's going to insert it into that third node because it goes down to the leaf. And if I try and insert 75, it's going to see that this is full. It'll split 60 on the left, 75, 80 on the right, and it'll pull 70 up. And in this case, it's slowly filling up the root node. And then let's try and really fill up the root node. Let me put 90 in. And then let me put, say, 78 in there. So 78 will slot between 75 and 80. This node will be full. So it's going to have to split it, 75 on the left, 80 and 90 on the right. That middle one will get pulled up. And then we'll have to do the exact same on the root. And the exact same on the root will be 20 on the left, 70 and 78 on the right. And then that 50 will be pulled up. So you'll see this happen twice now. So do you see what I mean about the tree essentially grows upwards? Like it's all kind of flat at the leaves, and as you add more, they all try and go into the leaves, but then it gets split and pulled up like that. Jeremy says, how does it decide? Well, it's the one in the middle on the left. I describe it to people like if you have in C, if you have 4 numbers in an array, like 1, 2, 3, like 5, 6, 7, 8, and these are all at like index 0, 1, 2, 3, and you say find me the middle element, the middle element's going to be 3 on 2, which is 1.5, which is 1 when you floor it. Because in computer science, often we floor things, is how we think about it. So the index ends up being this. So that's kind of a more philosophical reason we'd pick the left one, just in case anyone's curious. It's because it's kind of the midpoint if you try and represent the midpoint as an integer. I'm not 100% sure if that's the literal reason it's true, but it definitely makes enough sense to me for me to tell you that. Sorry, so someone's pointing out... okay, yes. That's a great point. So Vincent, thanks for that. I'm sure a couple of other people noticed it. So in these slides here, it appears that they're moving the one on the right up. Is what I'm get. Is that true? Because here they're inserting J and C's going up, but here they're inserting C and M is going up. I don't know. That's weird. Yeah, let me look at that one again. That's quite strange. These are just pulled from some previous slides, so I didn't overlook that. I didn't look at that closely enough, I guess. Yeah, let me go make a note of that or correct it or something. Okay, here's some pseudocode. Let's take a break. Let's take a 5-minute break. We'll do this for another 10 or 15 minutes, and then around 3:30 we'll talk about assignment 1. So yeah, 5-minute break, and let's get back into it. Hi, welcome back from the break. See, Izzy choked on a biscuit. Sorry to hear that. Okay. Spent another 10 or 15 minutes on this. Let's just talk about the algorithm briefly and then get into the complexity things, which I think is the really interesting part. So firstly, with a 2-3-4 tree, here's the pseudocode. You can go through this in your own time. The search one is quite straightforward. It's like if you're looking for a certain item in the 2-3-4 tree, the tree's empty, it's null. And what you do then is you essentially you follow a two-step process, which just consists of you scan through the node with all the items. Yeah. And I feel like your pseudocode's written slightly weird. It makes sense, but it's confusing. But essentially, you scan through all the items, and if you find what you're looking for, you're done. And if you haven't found it, then you just find the gap in the middle, right? This is very hard to represent concisely, I think, in pseudocode, but functionally, it's just like a binary search tree search, except you have to choose which branch to go down with a few instead of two. But then you also just have to iterate through the node itself. Waleed says, are we supposed to know how to implement this one, or is it just knowing how it exists and doing operations visually? I just want to answer that question broadly. Pretty much there's stuff we teach in this course that we go through really concretely with code, and then there's stuff like this which we teach with here's the patterns, here's the pseudocode, but we're not giving you code. Typically stuff like this, like AVL trees, like some of graphs next week, it will come up in quizzes and multiple choice stuff, and then some part of it, some of those topics might come up in a bit more detail in an exam or in an assignment, but generally that might be a quite selective thing. So I don't have a specific answer on this one, but generally you know, like if we chose to put it in assignment 2, then yes, you'd need to actually know how to implement it. But to be honest with you, the implementation of this one's actually not too bad. I don't think it's like, I think once you start to implement trees in general, it's all pretty okay. Like AVL trees is just storing some stuff here and doing a couple of rotations. If you're able to print out a tree and do some tests on it, then you can pick up on it pretty quickly. The actual insertion though is a little bit more lengthy, and what you can kind of see here is that if you insert into a tree with an item, if the tree's empty, you return a new node. But then what you do is you go and find the node you want to insert into. So you essentially use the search function. Sorry that the S is capitalized here. And that's that finding the leaf thing we talked about. Then you get the parent. Now, yes, in pseudocode, we're just like, oh, you have the node, get the parent. In a real data structure, you probably won't have the parent baked in. Maybe you'll add it if you want. I don't think we put it here. No, but you could always put it in the data structure. Remember, adding in things like parent links, add more memory, decrease like the complexity of some algorithms and might increase the complexity of others. It depends what kind of things you're doing. So you find the node you want to insert into, then you find the parent. If the node you're inserting into has less than 4 elements already, then you just simply insert into it. Like that, you just go, numbers in. Easy done. If it's not, then we have to node split. And node splitting is, you're on the node, which now has 4 values. You promote the middle one, so that's what you decide which one you're going to promote. You choose which one is like your new left node, and you choose which one's your new right node. And then essentially you just have to go through a series of processes of like splitting and stuff. And you'll see this code is written differently online. But this is where you go through that step of the middle, the new left, the new right, and then you have to insert it as the parent. And there'll be a recursive step here, which is this one here. So this if item is less than promote and if item is greater than the promote is essentially just a step of like where do you insert the new item? Is it in the left split or the right split? And then this line here, the other insert, this is actually inserting it into the parent itself. Is like taking the one you wanted to promote and moving it up to the parent. So curious little piece of code. I think the like a B tree insert or a 2, 3, 4 tree insert is a little bit more complicated than your standard algorithms. That's for sure. But generally, it should make sense. And more importantly, if you can visualize it through a tool like this, then you will find you'll figure it out conceptually. So just to loop back, so Waleed asked a question about this line again. So it's like node equals search. This is finding the leaf. So because remember, a B tree insert starts at the root, like all tree everything does. It looks for the leaf, tries to insert it there, and then it tries to build, you know, if it has to split, it'll keep splitting up until everything's good. So that's the actual find the leaf step here. In terms of the data structure that a 2, 3, 4 tree or a B tree would have, it would be a data structure like this, where essentially you have your node struct, and you would keep a few things on this node struct. You would keep the number of items you have in that node, typically, because arrays in C don't keep track of their own size. You would then keep a list of integers for the actual items in that node, and then you would keep a list. This is a list of pointers to struct nodes. So this is the child is a list with 4 items, where each item is a pointer to a struct node. So that would be your data structure. And depending on whether it's a 2 node, a 3 node, or a 4 node, that may be blank. So like you'll see these question marks here referring to that there's nothing quite there. So the data structure is pretty easy. It's just an expansion of what you're used to. It's like an AVL tree. We're just storing more information per node, just a different kind of information. And then just to loop back to this last question here. So Waleed says, but back to this node equals search line. But if we are inserting something that doesn't exist, why would that be in the tree? So I think it's important to understand that the search in a B tree or a 2, 3, 4 tree is slightly different from a search in a binary tree, because like when we say search here, what we're really saying is find me the bottom node in the tree that I would expect to see this in. So in this case here, search is, and you can see this in the return, it actually says return the address of a particular node. So a normal search is kind of looking for true or false or something like that. Sometimes it's, you know, finding a particular node or a new spot that's been created. But in this case here, you said if we're inserting into a tree that, yeah, it doesn't have anything, then we're essentially, search is looking for the spot that it should be, is the short answer. Vincent says, the question mark's null. Yes, so these are nulls. So in this case, the order's 3, which means there's 3 children, and 2 data members. So this order goes up to max 4 because it's a 2, 3, 4 tree. So the biggest node you can have is a 4 node. Now, we touched on this before. Searching a 2, 3, 4 tree still has a complexity of O log n. Please remember that log n and h are the same thing because the height of a tree is log n, so OH is the same as O log n. I kind of talked about this at the start. However, the logarithm is bigger, which means that the search complexity is effectively faster for a 2, 3, 4 tree. For insertion into a 2, 3, 4 tree, it involves a few different steps. Firstly, searching for the leaf node to insert is O log n or OH. If it's not full, we insert it in and that's O1, and that's easy enough. I think that should say if not full. I think I meant to write if is not full or if is full, not. So this one here says should be if it's not full, you insert into it, which is O1, and if it is full, you node split and create 2 new nodes, which is also O1. Even though it's a few steps, it doesn't change no matter how big the tree is. Like doing a node split on a node in a tree with 1,000,000 items versus a node split on a tree with 3 items still takes the same amount of time. So that operation does not grow in time complexity with the size of the data structure or input. So that's why it's O1. However, if you have to node split on everything from your leaf all the way up to the root, then it's O log n as well. So as I mentioned earlier, I said earlier that it was OH plus OH. Whereas here we're talking about it's O log n plus O log n. Same kind of thing. It's like, it's effectively, in the worst case, takes twice as long as just a standard binary search tree. Because it's a 2 log n, but again, we ignore coefficients for big O complexity. And then lastly, you can have other types of trees. You can kind of understand most trees as what we call a B tree. A B tree is just it's a tree with children and nodes that have a certain number of items in it. It's just that how many items and how many children. So binary search tree is a B tree of order 2. That's kind of why this visualizer only has these different orders or degrees or branching factors. It's all the same thing. Is because max degree of 2, you should just go use the binary tree tool that they have. So a B tree with order 4 or degree 4 or branching factor 4 is what we call a 2, 3, 4 tree. But there are other trees out there with like, branching factors of 6, for instance. So this one won't do a node split until it actually has a 6th item added to it, etc. So all these different structures. Now, there's been some good questions come up, and please reshare them again. I saw people were chatting about it over the break as well, which is around, is this faster? And like, why would you, like, okay, Hayden, if this is faster, why would we not just have a B tree with like a branching factor of 10,000? That's a great question. So if you think about a B tree, like this one, where is it? This one here. If you were to try and draw this as a binary tree, there would probably be a 4th level on it, at least, right? So if you're looking for The short summary I'll give you is that if you're looking for a node in a 2, 3, 4 tree that requires you to go through all like lots of the items in each node, then that's quite slow. But if you can avoid going through the items, then it's really quick. So if you look at a tree like this, checking if A's in the tree is really, really fast, because you go, okay, J, A's less than J, A's less than F, A, done. 2 levels. If this was a binary tree, you would probably end up maybe going 3 levels down or 4 levels down like that. So what it does is if you can kind of just run down certain paths without having to kind of check all the items in a node, then it's definitely quicker for those cases. It's not quicker in a big O complexity sense because we're talking about coefficients quicker, but it is quicker. So a B tree like that would have many less steps to find particular nodes. Where B trees can get quite complex though is that the actual searching through a node is essentially linear, because you have to go 1, 2, 3. There's no like binary searching it necessarily. I mean, I guess you could. I don't know. I guess if it was big enough, but that's a nightmare. So the thing is as the items in the nodes get bigger, it takes you longer to traverse through a particular node, because you have to iterate through every element in that node. So that's like one thing to keep in mind, is that's where, as this data structure gets bigger, for things where you can just kind of go straight down with doing minimal iterations through the items in a node, they're absolutely quicker in a coefficient sense. For things where you have to iterate through the node itself, then that's definitely slower. And just to give you like a really dramatic representation of this, if you had a B tree of like branching factor 100, this would just look like a linked list, because you would need like 100, that's the worst list I've ever drawn. You would need 100 numbers in this data structure before you split it. And what does that mean? That means if someone tries to look up anything, what happens is they actually have to just like iterate through this. And again, I know some people could be like, oh, we could binary search it. Sure, but like at what point is your algorithm getting too complex and stuff? So that's the kind of thing to take into account. Are there any other questions I've missed? If you have questions, now's the time to ask them. We'll do a few more minutes of questions, and then we'll get set up to chat about assignment 1. I'll just give it a sec, because I know it takes. What is the real world use case of this? Well, it's pretty much going to be faster to do lookups on average, because you don't have to run down as many branches. So for very large data sets, you could see quite a notable. You could see a realistic like 2 times speed up in the data structure. I remember a lot of sets are implemented as trees, and there's always a demand in computing for set operations to be as quick as possible. Autumnal says, at some point can we go through some examples of what tree is best in certain circumstances? We've done a few trees, but not really when to use them. Yeah, sure. Let me put that on my list. I'll probably try and do that. Might crowdsource something like that with tutors and just put up a page somewhere, because that sounds like a good idea. Yeah, so, and I like Keeson Verisid, yeah, so it says on the YouTube chat, I remember someone telling me that this sort is better if the data is sorted in a hard drive or something, where random lookups are way more expensive than sequential lookups. Yeah, so this is also why it's hard for like me to give a real summary table of things, where it's like, this is the use case. Like, if I was to give you something, I wouldn't really say like, these are the use cases. You'd use a B tree for this thing. It's more like a B tree has these advantages and disadvantages in these circumstances, and every kind of use case is different, because like as I said in the chat here, it's like there are some instances where random lookups are more expensive than sequential lookups. Like computers can sometimes do array iteration really quickly, and there was that great forum post by I think Matthew about a branch prediction in CPUs and stuff. And reality is like this stuff will never be of interest to you unless you go do some high performance things. And people who work in like high performance algorithms and stuff will tend to know a lot more about computers or spend the time researching more about them in terms of, some servers, for instance, have extremely cheap memory, and other servers have extremely cheap processing, and certain algorithms can be quicker if you can use a ton more memory. Like if you can cache things, like if you have enough memory, you wouldn't even use a tree a lot of the time, because you can just cache everything. It's just sometimes that can be more costly. So that's kind of why when we do these lectures, we say things like, all right, well, I mean, I know this one doesn't have a ton of like the specific use case, but I know some of the others do, where we're talking about, okay, well, this reduces the branching factor, which, means you're jumping around pointers less. Sure. And it also depends how you construct it. Because some things, like some trees, would be really expensive to construct. So like AVL trees with all these like rebalancing, the nature of the data that you insert might be so random that the tree's relatively balanced anyway. So like, do you really need to go to all this effort and add all this potential complexity? If your operation just needs you to insert, it's, so understanding the dynamics of these algorithms is kind of critical. Like that's why we do best case, worst case, and some things like that. Something like this as well, which I kind of didn't mention, I guess, is that this uses a lot more memory. Well, a lot more. I shouldn't say a lot more. This uses more memory, maybe less even, because you've got less nodes. So I guess there's less pointers you're storing. Probably less. If the nodes are filled, less, definitely, right? So that's what I mean. Like, here's another thing. Does this use more memory? I don't know. Are the nodes filled? Like, if all the nodes only have one item in it, if they're all two nodes, then essentially what's happening is that you've got all these this array that's been allocated. You've got this order that's been allocated. The struct is a fixed size. But if you fill it up, then you're kind of helping yourself in a way. Maybe not. No, I don't even think you are. It's probably always going to use more memory. Because a 3 node would have 2 data items and 3 pointers. It's often going to use more memory is what I should say. I'm not 100% certain if it's always going to use more memory. Because I guess if they're full, then maybe there's one less pointer you need to store. Because like, if you think about it, two nodes require 4 pointers. So that's like an int and pointer int. So that's 2 ints and 4 pointers. Whereas a 3 node stores 3 pointers and 2 ints. Plus the order number. So in that case, depends what the size of the int is and all this, like, is this an unsigned int? Because you could make this a really small number. This doesn't need to be an int. This could be a char. You could use a you use a 1 byte size here, right? Like you could use something. I don't know if there is like a small int. I know small ints are like 2 bytes, but this is a rabbit hole, So teaching fundamentals is quite critical because then you can go away and think about things like this. Great. Let's wrap that up there. I'm doing this a different way now. So here's my feedback QR code. If you could scan that, I'm going to spend a minute or two. I just want to bring Kevin into the call. Hope he's okay coming into the call. Plus, it'd be good to see his face. Oh yeah, because he can answer it verbally. That's why he's coming to the call. So if you could fill this out and I'll put you on standby for a sec while I just get everything set up. So thank you.